But let's try and solve or set up the solution to the problem I had, okay? And so we had pressure in kPa, and we have temperature in degrees C. Now, those are just text boxes as headers to a table. Now I'm going to put some numeric values in, 10,000 and 440, true? And maybe I would like to know what is the enthalpy in units of kilojoules per kilogram. That's all just a header, text box. And I come down, and if I had a routine, a function to help me calculate that, that'd be great. Well, I've loaded up with the help of other people in the University of Alabama software, which I show you how you can download and put on your own personal PC with that link right there in the design project handout. You just have to know the syntax. So we say, okay, I want to evaluate a function, start with an equal sign. I'm looking for the enthalpy. It starts to help me guess it, but there's just a whole lot built in, isn't there? But the syntax is usually an underscore with the pressure temperature, underscore H2O, parenthesis, that's my function. Click on the pressure, click on the temperature. Now, it assumes the pressure and temperature in particular units, kilopascal, degrees C, and it gives back enthalpy in particular units. If you're ever at a loss, come up, you have that function right there, hit this function key, and it tells you, oh, you're trying to evaluate this function called H underscore PT underscore H2O. You're trying to give it a pressure in cell C5. The numeric value that I currently find in cell C5 is 10,000. You're trying to feed it temperature in cell D5. The current numeric value is 440. And you haven't put any comma with units because you can work in English units or pounds and BTUs, but I don't regularly do that. I leave it off. And currently, if this is to be evaluated right now, it'll return a value of 2,314. And down here it'll comment, hey, enthalpy in kilojoules per kilogram is a function of pressure in kilopascal and temperature in degrees C. That's the SI units. And if you put the optional ENG for English units, then I want BTUs per pound mass for the enthalpy, PSI-A for the pressure, and degree F for the temperature. So there's the resulting, that's repeating the information. So there's a lot of information available to help you. Let's evaluate entropy, lowercase s, comma, kilojoules per kilogram Kelvin. And you would say S as a function of pressure temperature for H2O, and grab pressure, comma, click on temperature, and away you go. A lot of times I like to put what state it is, that's state 1. How did we go to state 2? Well, state 2 was 1,000 kilopascal, wasn't it? And it was isentropic expansion through that turbine, true? So the S2 is equal to that value of S. So, and if somebody says, no, it's not 11, it's now 11 megapascal, you put, and then it updates all the way through. But let's go back to 10 megapascal. Whoops. Okay, there you go. I want to get that enthalpy. Well, it's not a function of temperature and pressure and temperature, it's a function of pressure and entropy. Let's try that. Equal to H, a function of pressure entropy. And then, you know what, after a while you start to see it's highlighted. They want to help you fill it in. If you just hit tab right there, that one that's highlighted is filled in. True. And then you hit this pressure, and I really need G6. I can type G6 right there, and it'll grab it and evaluate it. All right. Or I could do H as a function of pressure and entropy. Tab. Okay. I can grab this one, comma, and I can try to click on that like I clicked on this one. But the problem is it's hard. Sometimes I click in a box around it, then I kind of grab it and tuck it underneath. Anybody ever had that experience in Excel? We kind of want it underneath there. It's blocking itself. And so you just kind of get it there and then tuck it underneath. Otherwise, I found that very frustrating. There's another way of doing it. Just expand that thing way out here and then, oh, let's try it again. I want to evaluate enthalpy. It's a function of pressure and entropy for water. Hit tab. And there's my pressure, comma, and my entropy is, it's still covering it up, isn't it? I don't know why it's still covering it up, but I grabbed it and tucked it in, hit parenthesis and be done. Okay. What was state 3? Oh, also I like to put a little column out here about what properties fix that state. That was pressure and temperature, wasn't it, for state 1? Pressure and entropy for state 2. What about state 3? Didn't we go all the way to 10 kPa? 10 kilopascal. Is it entropy again? Isn't it isentropic expansion through the turbine? Okay, and now this is another beauty of Excel. If I've already typed that formula, I'm going to type that formula again, and what I can do is I can just do a Control-C on that formula, bring it down here with a Control-V paste, and it actually saves the relative location of the pressure and entropy, such that, let me hit escape, that this guy grabs it from this line for pressure and entropy, but this one, where I copied, it grabs the same line, it's on line 7, for the pressure at 10 and the entropy over there. So it's pretty smart. Ooh, we need to evaluate these temperatures, true? The other thing is I could evaluate quality, X. Well, let's do this. Let's do the quality as a function of pressure and temperature for the quality, pressure, and temperature. When it doesn't give me the formula like that, I have to look around a little bit, okay? Looks like I'm going to use pressure and enthalpy to get the quality. So I'm going to hit tab there. I'll get the pressure, comma. I'll tuck in the enthalpy, close it. And this is just a drawback a little bit. That quality comes in 1. That doesn't mean it's saturated vapor. It just is, they didn't want to put not defined, but that's definitely superheated steam. So you really need to be cautious. Excel is okay, but it's not smarter than you. It's actually dumber than you. And you have to know, oh yeah, this is they're just returning a number, not blowing it up and making it undefined like I can't continue. But I don't trust that. It's superheated steam. All right. Now let's do this. If I take and copy that formula and I paste it right here, I see the quality is 95% at state 2. If I paste it right there, it's 76%. If I want to have these look like percentages, come up to this number. It's under home, number, hit percent, and it makes it look like percents. If I want to adjust the number of digits, just adjust the number of digits. Similarly here, that seems like it's excessive number of digits. It cleans up my digits here. This looks a little excessive. Ooh, more excessive. So you can make it very visually appealing to you, and so it's easy to read. How about this? Let's get the temperature as a function of pressure and entropy. Will it allow me to do that? Sure. For steam. So there's the pressure, and here's the entropy. And notice that's coming in right there. I could also say, I'm just going to show you something. What is the temperature for saturated liquid? Ooh, it doesn't like that. How about sat? So I have to somewhat guess the routine. The temperature of saturated liquid as a function of pressure for H2O. And we'll use this pressure right here. And notice that temperature is the same as that temperature. So in the two-phase region, it's giving me back the saturation temperature. If I just grab this lower box right here on this cell, if I grab it right there and I drag it down, it brings that formula down. I could do cut paste, or I could just drag it down. When you have a long column, a lot of times you drag a long way. Okay. So the temperature at 3 is 45.8. Let's get rid of this. What was 4? This was a pressure and entropy. What was state 4? That was coming out of the condenser. It's pressure and saturated liquid, wasn't it? So they say, how am I going to do that? Well, I can reference this cell right above. So it's 10 kPa, or I could retype it. And it's saturated liquid. I need that enthalpy. How about HL? Will that give me? Yeah, sometimes the syntax you have to think, okay, it's HL. Enthalpy of saturated liquid is a function of pressure for H2O. Come over at 10 kPa, close it. There you go. Too many digits, move it over. Okay, how about the entropy, saturated liquid as a function of pressure, H2O. Boom, there you go. And then you could put also the Tsat, function of pressure for H2O. Put the pressure there. See how you're building this out? How about quality? I guess we'll try quality. Do a copy, paste. Hey, it came in with 0%, which makes sense.
Is there any specific reason we're doing this on sheet 2?
Nope. And what you can do is go down here and click sheet 2, do a right click, rename the sheet and say main sheet. And then you don't like this sheet, click, come up, right click, delete that baby. So you clean up. You want to insert a column over here, insert. You want to insert a row right here, insert. So once you get good at inserting and moving things and making it clean up, and you can control. You can also delete, like I don't want those. Hit right, delete, bye-bye, or whatever. Now let's go to state 5. What was that? That was after our pump, wasn't it? It's going to be after the pump. Well, if our pump is going to boost us up to what pressure? 10 MPa. And here's the thing where doing it by hand will divert a little bit from the code. The pump is reversible, true? Is the entropy the same? It is. And here's the little advantage of the computer software, because now this state 5 is fixed by pressure and entropy, true? It's just like 2. What I could do is I could copy these 3 cells, just paste them right there, and it shows me, first of all, it's now compressed liquid, so 0%. That's just like 1 for superheated vapor. It's not saturated liquid. It's compressed liquid at 5. But there's the enthalpy calc, and there's now the temperature. Notice the temperature is slightly a little bit greater than the temperature at 5. There is a little warming. The temperature does go up a little bit, but not much. About what? Less than a degree. What is that? 0.3 degrees C. That's not a lot. Somebody says, I thought we were going to use V times, P 5 minus P4. You can do that. If you do that, I need the specific volume in units of meters cubed per kilogram. True. Let's go get the specific volume at state 4. V is a function of, V liquid. Does that work? Yeah, that'll work. As a function of pressure. So there's our specific volume. Notice the, it's a small number, 0.001010. That looks reasonable to values out of the table. And if we multiply that, so I want to evaluate V times the change in pressure, 10,000 kilopascal minus 10 kilopascal, I'll get the work of the pump. It's around 10.09 kilojoules per kilogram. True? Here, if I wanted to know the work of the pump, it's going to be the difference between this minus that. And if you do a little comparison of these numbers, they're not perfect, but they're good to almost 4 digits. So the way we were doing it by hand, VDP gives you 10.09. Doing it using this built-in software with constant entropy, it's 10.06. close enough. As a mechanical engineer, at times you should say, good enough, right? Good enough, close enough. Let's go to state 6 now. What was state 6? That was coming out of the feed water heater, and it told us that it was at this pressure, and the temperature was it 170? So basically we're back to knowing the pressure and the temperature. I come up, I don't like to retype a lot, so I just grab those cells. Whoops. Grab, hit escape. When in doubt, hit escape. I'm going to do this, and I'm going to do paste right there. So that evaluates the enthalpy as a function of pressure and temperature at state 6, as well as the entropy. What about state 7? What was state 7? Was that the saturated liquid coming out the bottom of our closed feed water heater? So it's pressure in saturated liquid. True? Okay, so the pressure was 1,000 and it's saturated liquid. Well, you could probably grab these right here, bring those down, and that'll fill it. So it's the enthalpy, the information we really look for is that enthalpy, and so there's that enthalpy. And you can compare it. Okay, notice what is the enthalpy of the sum of the steam that was diverted at 2 that came into the top of that closed feed water heater. What goes out is the enthalpy here. Look at the enthalpy difference. There was a lot of heat transfer from that warm fluid heating up the fluid going from 5 to 6. All right. Let's continue on. What is state 8? Well, that was back to our low pressure and our enthalpy. True? Isenthalpic. So it's back to 10 kPa. And our enthalpy, what is our enthalpy? Is it 7? So there you go. Those two fix the state, knowing pressure and enthalpy. So I could look up temperature. Here's a question for you. Will that temperature be less than 180, greater than 180, or equal to 180? So we want to find the temperature as a function of pressure and enthalpy for water. There's our pressure. Here's our enthalpy. Last chance to guess before we go. Look at that. Why is it, and that number rings a bell. Hey, doesn't that number look familiar? Have I seen 45.8 before? It's actually two-phase. It's two-phase, state 8. And then you dump it all into the condenser, true? You dump it all into the condenser. So now that we have all of these, I have my property table figured out. True? I can maybe make this bold if I want. Bold. Clean it up a little bit with some pretty little formatting if you want. Something like that. I'm going to do this. I'm going to grab all of this to the side and I'm going to delete it. Just hit delete key. It's gone. And I'm going to start my calcs over here. And one of the most important is that mass fraction that's diverted. What is the equation for that? Was it H6 minus H5 divided by H2 minus H7? Was that what it was? So it looks like for this problem, 27.17% is of the mass that's through the first turbine stage gets diverted down, leaving 1 minus y, which is simply 1 minus that. Now you say, why does he make such a simple calc? Often with spreadsheets like that, you just go ahead and evaluate that as 1 minus y. That way when I need it, I don't have to always do 1 minus something. It's available. It's 72.83%. Okay, let's do this. What's the work out of the first turbine stage? Was that H1 minus H2? All right. What about the work out of the second turbine stage? Is that H2 minus H3? Now, this one I'm going to put a little note. This is per kilogram going through the second stage, second turbine. Now, but I really want to put everything on per kilogram that went through the first turbine stage. So the work, second turbine stage per kilogram of turbine 1, if that syntax makes sense to you. And what I do is I say, for every kilogram that went through the first turbine stage, only 0.72 kilograms goes through the second turbine stage. So I'm going to take this value and multiply by 1 minus y, and now I have that work that comes out on the same kilogram basis as this one. They are on the same kilogram basis. Subtle but important point. Then we go to maybe, what is it, Q in the condenser. So what is Q in the condenser? Let me back up and show a slide here. In the condenser, you can think about this stream being condensed and this stream being condensed, true? So Q of the condenser is the sum of two parts. It's the sum of 1 minus y times H3 minus H4 plus y times H8 minus H4. Okay. So let me go ahead and implement that equation in the Excel. So it's equal to 1 minus y times, it was H3 minus H4, true, plus y times H8 minus H4. Does that make sense? So this is how many kilojoules of heat is removed from the condenser per kilogram that goes into the first turbine stage. Let's do this one. What's the work of the pump? Well, is that going to be the H5 minus H6? That many kilojoules per kilogram? Yeah? Okay, take a look at the illustration again. 4 to 5. So 5 minus 4. Is that what I wrote? It's G6. You could if you double click this right here, it'll even highlight the box. Did I misspeak? Okay, I misspoke, but I got the right box. Thank you. All right, and then what's the last one? What is Q in the steam generator, right? And so it comes in and goes out. It goes out at H1, and it came in at H6. True? Is that right? Now, when you do this, calculate work net on the same per kilogram basis. Work net would be you have the turbine 1 plus the turbine 2 on the same per kilogram basis minus the work of the pump on the same kilogram basis. So it's about 1,003. How about Q net? And they better equal, or I better look for an error. Because, yep, that's what it is. So it's going to be the Q into minus the Q out. And they agree. And kind of funny that it agrees to a lot of digits, doesn't it? That's nice to see. All right. What about the back work ratio? That's going to be the work of the pump divided by the net out turbine 1 plus turbine 2. And the thermal efficiency, what is that equal to? It's equal to the net work out divided by only the heat in, not in minus out. So only the heat in from the steam generator. And we could put both of those on percentage basis, and we find that it's 1% back work ratio and 40.3% on the efficiency for the plant.